You just finished administering a psychological assessment. Your subtests are in the low average range, but your composite is below average. What happened? Was there a problem with the test, with your scoring? This is an expected effect of psychological tests. We'll talk about the explanation behind why this occurs and how you can explain that to the people involved with testing. Hi everyone, I'm Brian Syzdek. I'm the product manager at Stoelting and a clinical psychologist. Stoelting is a publisher of psychological assessments. We're going to talk about an effect that occurs in psychological testing wherein the composite of subtests ends up being more of an extreme score than the subtests themselves. So I often get some questions from people about they've administered a test and they find that subtests might be in a certain range. They tend to be within the same range, and they find that the composite does not correspond to like the average of those subtests. For an example, let's start by looking at the Lighter 3 International Performance Scale. It is a nonverbal intelligence attention memory test, and let's just focus on the IQ subtests from that test. We've got 4 subtests. And let's assume in this example that this individual scored all 8s on those subtests. Now, the subtests follow scaled scores, so we've got a mean of 10 and standard deviation of 3. That puts all these scores within the average range using the Lighter 3 classification criteria. Now, when you go to find the overall nonverbal IQ score, which is made up of, it's simply a sum of those scaled scores, and then that corresponds to an index score, you find that the index score for this individual is an 81, which is below average. And remember, index scores have a mean of 100 and standard deviation of 15. So this may appear puzzling initially. You know, the person on those subtests was performing average, though on the low side of the average range, but their overall nonverbal IQ was below average. That doesn't seem to correspond to what you would be expecting. How can this be? How is the index score below average? Well, we're going to go over that this is actually an expected phenomenon. It's a feature of intelligence, psychological assessments, and not a bug. So I'm going to give you some explanations so you can understand why this is occurring. We're going to approach it from a few different levels. We're going to start by talking about how this can be looked at as a case of regression to the mean. We'll go over how to calculate index scores, and we'll cover a geometric interpretation of why this is occurring. So you're going to have a few different ways of looking at it, so you can find the way that resonates best from you or deeply understand it. And then we're going to go over how you can explain this to stakeholders in the testing. So first of all, let's think of this phenomenon as an example of regression to the mean. And the first thing to understand about testing is when we use category labels, we use those for convenience and understandability to aid in test interpretation. But, however, whenever we take some continuous scores, whether they be subtest scaled scores or index scores, and we convert them to categories, we're losing information. So even though we say on subtests that a score of 8 to 12 is in the average range, that helps us understand that. That gives some meaning to those scores. But we're losing information because within that 8 to 12, there's differences. A score of 8 is different than a score of 12. And similarly with index scores, we call 90 to 109 on the Lighter 3 an average score. And a score of 90 is different than 109. You know, it's kind of like looking at the day as either a cold day or a hot day. Well, you know, if it's above freezing, that might be considered a hot day, but that's a lot different than a 100-degree plus day. So we use those categories to help us, but there's some limitations. And that the other thing to know about regression to the mean is subtests and composites indexes are normed separately. So we calculate the scores separately. It's not unusual for a person to score below average, like an 8, which is at the low end of average on one subtest. It's not unusual for a person to have a low score, below average on one subtest. Um, what is more unusual is for that pattern to repeat on several subtests. So even though it may be at the low end and be considered average, it's slightly below the mean. And when that pattern repeats, getting an 8, 8, 8, 8, that is more unusual than that just occurring one time. So another way to say that is multiple low average results lead to below average overall, a more unusual overall profile. Think of realistic examples. It's maybe not so unusual for a person to excel in one ability, say for a person to be proficient in a certain musical instrument. It's more unusual for a person to excel in multiple abilities, like being master at several musical instruments, or in sports, a person might be a good hitter or a good pitcher, but it's quite unusual for them to be able to do both really well. And so that's what we see occurring in composite scores, is that the cumulative effect of slightly differences is more extreme than just the average of those differences. Let's also get into how we calculate these index scores, so I can show you, so you can see and understand mathematically why there's a more extreme composite score. When we look at standardized scores, what we are doing is taking a score and subtracting the mean and then dividing by the standard deviation. You can conceptualize this as the difference of some score from the mean over standard deviation. So we're like saying how many standard deviations away a certain value is. For example, scaled scores has a mean of 10 and a standard deviation of 3. So we take whatever score it is, subtract 10, divide by 3. We can also convert across different scores, different scales. So the way we do that is basically by equating what the values are for these different scales in terms of mean, standard deviation, and one score that's obtained on one scale, and then how we can solve for the score we need to know on another scale. So subtest raw scores, we would find the mean for everyone who's taken the test, divide by subtest standard deviation of everyone, and convert that to a scaled score for a particular scale. There's a function that we can use to just plug in values, and all the code that I use for these slides and will be available at a link in the show notes. You can use that to make your own scaled scores or other scores that we use. And let's consider an example. So we'll use that function to look at what happens with someone who scores a 10. And let's say on this particular score, on this particular test, we find that the mean of everyone who took the test is 20. The only difference is in subtest 1, we're going to say that has a standard deviation of 5. And in subtest 2, we're going to say that has a standard deviation of 10. And we're going to convert these to scaled scores. So what effect does it have having a different size standard deviation? And we can see at the bottom in subtest 1, we end up with a scaled score of 4. And in subtest 2, we end up with a scaled score of 7. So what conclusions can we draw? Everything else being equal, holding everything else constant, a smaller standard deviation is going to lead to a more extreme converted standardized score. Why is that? Why is a smaller relative standard deviation, smaller relative to all other values, lead to more extreme standardized scores? Well, look on the left side of this equation, and remember what we're doing when we're converting across scaled scores is we're looking at the difference from the mean from one scale compared to the standard deviation from that scale. And let's say that the standard deviation of some raw scores is smaller relative. How does that affect the inequality? Well, we know in fractions that as a denominator gets smaller, the effect it has overall on that fraction is an overall increase for that entire fraction value. Because of that, what do we need to do? The side on the right must be increased also to preserve the equality. We're saying these are equal, but the standard deviation's fixed on the right side. So standard deviation of standardized scores is set. If it's a scaled score, it's a standard deviation of 3. If it's an index score, it's a standard deviation of 15. So we can't adjust that. What we can do is adjust that numerator. We can't adjust the mean, but we can adjust what that standardized score is, how far it is from the mean. So we must increase that numerator. And what that does is, and what we need to know is that almost always, standard deviation of combined scores is going to be less than standard deviation of those scores individually, or just the sum of those scores. It may be equal to, but it's hardly ever equal to. It's almost always less than. And the way we standardize 2 subtests is similar to 1 subtest. So what we're going to do is just subtract raw scores from the mean, and we're just going to sum that for each of the subtests. And then we're going to divide by subtest standard deviation combined. Now let's look at how we calculate subtest standard deviation combined, because it is not just adding all the standard deviations. It's a little different. So we know that variance is just standard deviation squared, or going in the opposite direction, we can get standard deviation from variance by square rooting. And so maybe the first part of this equation makes sense, that we're just adding the variances, but this second part, this 2 times the covariance of subtest 1 and subtest 2, where did that come from? Well, that's going to make a difference here. And you can find out that it can be obtained, this formula, by expanding how we calculate standard deviation. I show below there that you just are subtracting from the mean each one of the values, subtracting the mean from each one of the values for all of your subtests here, x's and y's, and then you're squaring those. So it's the sum of those squares divided by n. And we can just expand this on the top, FOIL it out, and you can see that the first 2 terms, that x minus mu of x squared plus y sub I minus mu sub y squared, those are the variances. So that's variance of, if the x is subtest 1, variance of subtest 1 plus the variance of subtest 2. The second part, this plus 2 x sub I minus mu x, y sub I minus mu y, that's the covariance. So that's where we get the formula. You can find some videos that explain that more thoroughly. And the covariance cannot be greater than the variance of subtests. The greatest that the covariance could be equal to the variance. And let's assume this is possible. It rarely happens, but let's assume this is possible, that in this case, the variance is equal to the subtest, the covariance is equal to the variance of the subtest. What we get then when we plug in variance for covariance is we've got the variance of each subtest plus the variance of each subtest. And if these variances are the same, what we end up with is 4 variances. And when we square root, that simplifies to 2 standard deviations. So we could plug that into our calculation of index scores for subtest standard deviation combined, if we're assuming that the difference from the mean for both these subtests is the same, and the variances are all the same, and the covariance is equal to 1, then we end up with, when we simplify that for these 2 subtests, calculating the index score, we've got 2 times the difference from the mean over 2 times subtest standard deviation. And that's equivalent to the difference from the mean over the subtest for just 1 subtest, subtest standard deviation. But that only occurs when subtests are perfectly correlated. As the correlation decreases, standard deviation decreases, and the composite becomes more extreme. Now, subtests on a test, we want some correlation, but we don't want a perfect correlation. We don't want a 1.00 correlation, right? We want our subtest to measure slightly different things, and that's what happens when we look at the correlations of subtests on any given test. So the covariance cannot be greater than variance of subtests. And here's the actual formula to calculate. Usually we calculate covariance. A lot of times we'll have the correlation, or if you're looking in a test manual, typically they'll report the correlation and variance of subtests. You can use that to calculate covariances, so you can create your own index scores. And then when the variances are all equal, an alternative form of this calculation is that we can get the standard deviation of composite scores, so like two subtests. Let's say we have two subtests by standard square root of 2 plus 2 times the correlation over 2 times the variance pool. So if we have the same, not variance, standard deviation pool. So we have the same standard deviation. We can see that the only difference here between the standard deviation of one subtest, what we're calling standard deviation pooled, and the composite is this square root of 2 plus 2 correlation over 2. And again, what that does is, at best, we could hope for a correlation of 1. That would be 2 plus 2, 4, square root over 2 would break down to 1. So at most, if we have a correlation of 1, our standard deviation of 1 subtest would equal standard deviation of the composite. Let's look at an example. As I said, a lot of times you can calculate you can create index scores from subtests. And you can do that by finding the correlation and variance of subtests that are typically listed in the manuals. So in the lighter, we have an appendix I, broken down by ages, different correlations of subtests, and then the variances are listed in the bottom rows. And we can plug that into our formula, correlation equals covariance over the standard deviations, and calculate the covariance, which we need to calculate the variance for subtests. And just using this function or plugging it into the formula, in this case, we find out that our figure ground and form completion correlation based on this, what's listed in the table, is 0.73. There's a standard deviation of figure ground of 3.3, and for form completion, standard deviation of 4.5. We plug all those values in, and we calculate that the covariance of these two subtests is 10.84. Okay. What we can do with that then is plug that into that covariance part of the equation, and then the variances to calculate a combined variance. When we do that using this function, we find that our figure ground and form completion combined variance is 42.52. We can then plug that in. So let's assume that in our example, we said that form completion and figure ground, this individual scored an 8 on both of those subtests. We know that the subtest means are 10. So we plug that in, 8 minus 10 plus 8 minus 10. We're combining the subtest differences from the means. And then for our subtest standard deviation combined, we're going to plug in our combined variance, 42.52 square root. And then we're going to rescale this on the scaled score. So we need to set that equal to what the scale score would be minus the mean over standard deviation. And now we're just going to solve for what that scale score will be. So we're recalibrating two subtests to what would that be on one scaled score, so we can see how these two subtests combine. And when we do that, we find that the scaled score with those scores of 8 and 8 on figure ground and form completion would be a scaled score of 7.85. How does this compare to that scaled score of 8 on both those? We can see it's slightly lower. So we can see by this example, it's not the average of those two subtests. Everything was equal in our example, but here is a 7.85. Okay, and that's just with 2 subtests. What's going to happen is as the as the subtests number of subtests increase, that index score is going to be more extreme. Okay, so as standard deviation lowers, that's what happens as you add on more subtests. That standard deviation of the pooled subtests will lower. We said that then increases the extremity of that overall index score. And so what we can do, what I did here is I just went through and for all the 4 nonverbal IQ subtests on the lighter 3, I averaged across all the ages what the correlations of all those subtests were, all those subtests standard deviations. I averaged across, plugged it into this function that will calculate an index score. So now we're setting this equal to an index score with a mean of 100 and standard deviation of 15, and calculating what would this would equate to with 4 subtests with scores of 8. We find that the nonverbal IQ score using this formula is an 85. So we said earlier, according to the lighter manual, that would be an 81 for subtests with 8. Now, this is just, I'm using the scores that were presented in the back of the manual, which didn't break down how many people were by different age groups, which would have affected the correlations and subtest standard deviations and so on. So I was just doing a non-weighted simple average. So, but you can see the 85 is more than it's one standard deviation away, which puts it in the below average category. It's more extreme than those subtests. Okay, we've gone over how to calculate scores from the index. Now let's look at a geometric interpretation for this phenomenon of extreme composite results. The thing to note is that the cosine, we can look at subtest scores as being 2 vectors in a geometric space, typically like a coordinate system. If we look at those vectors as coming to an origin where the means of the subtests meet, the cosine of the angle between those 2 vectors is equal to the standardized Pearson correlation of those vectors, of those subtests. Okay, so we're going to go over what this means. So cosine of that angle is equal to the dot product of those 2 vectors. So we're just multiplying the corresponding entries of values from those vectors over the magnitudes of those vectors. Okay, and this, we can see what happens when we plot this. So we can see subtest 1 is in the red, subtest 2 is just along the x-axis in the blue. And these 2 vectors make an angle, and the cosine of that angle is equal to the correlation of those vectors. So as the vectors are spreading further and further apart, the correlation between them is going down, and the cosine of that is what the correlation is. Now this green vector is the composite score of those 2 vectors. And that can be calculated as finding the cosine of half the angle between those. And remember, cosine of an angle is equal to adjacent over hypotenuse. So we know that from 10 to where the blue arrow is right now at 12 is 2. So here we're looking at with scores of 12. This is a little easier to look at as we go into this positive space instead of looking at scores of 8. But it's the same. It's two scores away from the mean. So instead of 8, which is 2 points below average, now we're looking at 2 points above average. We're going to see that the same principle holds, and it would be the same scores as looking at 8s. And we can see that the composite increases as the subtests become less correlated. Okay, and looking at our same example of the figure, ground, and form completion, where we looked at the correlation of those subtests as having 0.73 when we calculated them in the index score, we find out that at that we could solve for that 0.73, find the angle that equals. So that would be the inverse cosine of 0.73. We find that's a 43-degree angle, and we could find out what the composite value is. That's that line bisects those two vectors and extends perpendicular to those vectors. So we've got right triangles. We can solve for that composite vector, what its length is, as half that angle. It's the cosine of half that angle is equal to adjacent over hypotenuse. Well, we know the adjacent is 2 from 10 to 12. So we can multiply that cosine of half that angle by the adjacent and get the length of that, which would be 2.15, which we're starting at 10. So we add and we get that score is 12.15. Now, what does this tell us? This tells us, remember, the red subtest line is 2 from the mean. So it's a 12, score of 12. And the blue subtest line is 2 from the mean. So it's also a score of 12. It's saying that subtest 1, the score is 12. Subtest 2, the score is 12. The composite is 12.15. Now, remember when we looked at when the scores were 8 and 8 for subtest 1 and subtest 2, remember that's 2 below the mean. What we found that is the composite score in that case was 7.85. What does that say? That was 0.15 more extreme than those two subtests. That's what's happening here, just in the other direction. The composite is 12.15, 0.15 more extreme than the two subtests. And when we calculate what the composite score is using our formula, where we convert the sum of two composite scores, difference from the mean, over their composite standard deviation, and then rescale on a scaled score scale, we get the same result, where that composite score, when you have scores of 12, is 12.15. And that was the same result, 0.15 from the mean, that we got when we looked at when the scaled scores of figure, ground, and form completion were 8. We got a result of 7.85, which was 0.15 more extreme in the other direction from those two scaled scores. So let's summarize. We went over a few different ways to explain and understand why composite scores are more extreme than just the average of those individual subtests that comprise that composite. We looked at number one, because of regression to the mean. It's even more unlikely to have several unlikely scores. So, one unlikely score is not as unlikely, but several is more unlikely that those all are occurring. And so that makes that composite score even more unlikely, even more extreme. We went over how to calculate an index score, and we saw that composite index variance or standard deviation will be almost always less than subtest standard deviations. At most, it could be equal to, but that only occurs when subtests are perfectly correlated, which doesn't occur in an intelligence test or any other type of psychological assessment. There's some differences between the subtests. And we saw that because of that variance that will always be smaller, that leads to a more extreme difference from the mean when we're scaling those combined subtests on that same scale as or even when we're looking at categories, which are essentially scale agnostic. They are standard deviations from the mean on whatever scale you're using. We also looked at a geometric interpretation, and we saw that as correlation decreases, extremity increases, so a more extreme index scale is obtained as the correlation decreases. And we saw that that composite vector extends out from those two subtest vectors. Okay, so let's go over how we might talk about this with stakeholders. Now, I think you'd probably not want to get into as of deep a discussion as we had here to explain this phenomenon of extreme composite scores, but I think it would be good to be able to provide some information. You might either present this information up front, or a stakeholder, parent, teacher might notice that, hey, these subtests that the student scored average on aren't matching up to what the overall score is. Why is this occurring? Well, I think there's some tips that I would have that I would typically want to convey to stakeholders. Number one, I would want to summarize the findings. And for example, going back to our example where this person scored scaled scores of 8 on each of the lighter subtests, and then there's this label of average. We talk about that, what subtests are, and that they comprise this composite. So we group these subtests together to form a basic construct that we call nonverbal IQ, that all these 4 subtests represent skills of. And on that overall composite, this individual scored an 81, which we label as below average. Now, I would have a little difference about a little explanation of what these labels are that we use to describe subtests. So I would say something along the lines of, we use a description of subtests to give some meaning as to what these scores are. For a score, there's a range of scores that we have a subtest label for. So for example, scores of 8 to 12 on subtests are considered average. Though we use this to help us understand about a subtest score, there's differences within these categories. So a score of 8 within an average range is different than a score of 12, though we call them both average. I'll then explain about why we see that when there's some small differences across many different subtests, that leads to a larger difference when we put all those subtests together. And I would basically say as much as that, that when we see small differences, one small difference on a subtest is unlikely. But when we see that repeatedly, that becomes a little bit more unlikely that those all happen. And even though there's small differences, when they're repeated, those differences become more magnified, become bigger. So we see that overall, those lead to a greater difference, which is what's happening in this particular example. So that's some explanation of why composite scores are more extreme than subtest scores. Hopefully this helps you understand as to why this occurred, and gives you some information about why the subtests are in fact doing what they're supposed to, and why you're scoring them correctly, and how you can explain that. There's some resources that are very helpful. This first paper give a great explanation of this phenomenon, using a lot of the same ways that we talked about here. If you have any further questions, please contact us at Stoelting. Again, my name is Brian Syzdek. I'd be happy to help you talk a little bit more about this. Thank you very much, and please let us know if you have any questions. Thank you.